There is something strangely unsettling about seeing a 60-year-old engineer become one of the most valuable people in the global economy. Not a billionaire founder, not an AI researcher in his 30s, not someone writing code from a coffee shop in San Francisco. A man who spent the 1990s arguing about contamination levels inside a clean room, troubleshooting yield problems at 2 in the morning, and figuring out why one layer of copper wiring kept failing during production. People like that are receiving calls. And many of those calls are coming from China. For years, the conversation around semiconductors revolved around machines. The Dutch company that makes EUV lithography systems, the American firms designing GPUs, the factories in Taiwan producing chips smaller than a virus. Washington built its strategy around restricting equipment, software, and manufacturing tools because the assumption was simple: deny China access to the hardware and progress slows down. That assumption still matters, but it may not be enough, because a fabrication plant is not a cookbook. You cannot simply buy a machine worth $350 million, unpack it, and expect world-class chips to emerge at the other end. Semiconductor manufacturing is closer to accumulated tribal memory. Thousands of small decisions, tiny adjustments, mistakes repeated often enough that someone eventually learns how to avoid them. And the people carrying that memory are getting old. We'll come back to one specific number later, 55. For now, just remember it. The engineers who helped scale American semiconductor manufacturing during the 1980s, 1990s, and early 2000s are mostly in their 50s and 60s today. Many worked at companies like Intel, Micron, Global Foundries, or suppliers embedded deep inside the ecosystem. Some retired years ago. Others stayed on as consultants because replacing 30 years of practical experience turns out to be harder than replacing a CEO. China appears to understand that. Since 2014, Beijing's National Integrated Circuit Industry Investment Fund, better known as the Big Fund, has poured tens of billions of dollars into domestic chip projects. Local governments joined in. Provincial talent programs multiplied. Companies associated with SMIC, Huawei, YMTC, and dozens of lesser-known firms began looking abroad for expertise. The salaries can be extraordinary. Several industry reports over the past few years described offers reaching 2 or 3 times what veteran engineers previously earned in the United States, Taiwan, or South Korea. Housing allowances, relocation packages, flexible consulting arrangements. It's a little ironic. America spent decades teaching the world that talent follows opportunity. China seems to have listened very carefully. There is a counter-argument, and it deserves to be taken seriously. Critics point out that experience alone cannot compensate for missing technology. A retired process engineer cannot manufacture EUV scanners. He cannot magically recreate restricted design software. He cannot reverse engineer decades of supply chain specialization. That's true, but I keep wondering whether we're measuring the wrong thing. Perhaps the question isn't whether these engineers can hand China the ability to produce 2-nanometer chips next year. Perhaps the question is much smaller. Can they shorten China's learning curve by 5 years? Can they prevent 10 expensive mistakes? Can they teach a younger generation what only becomes visible after watching several fabrication plants succeed and fail? Because if the answer is yes, then this isn't really about recruitment, it is about inheritance. And inheritance matters most when the people holding it are preparing to leave. There is one engineer in particular whose story illustrates this better than statistics ever could. He never became famous, rarely spoke publicly, and spent most of his career solving problems nobody outside the industry even knew existed. His experience tells us why 55 may turn out to be a more important number than 5 nanometers, and why America's remaining advantage might be much more fragile than it looks. For most people, semiconductor manufacturing feels abstract. We see the finished products: phones, laptops, data centers, electric cars. We rarely think about the individuals who spent decades learning how to keep microscopic defects from ruining an entire production run. One of them was William Holt. Holt joined Intel in the 1970s and eventually became Senior Vice President and General Manager of Technology and Manufacturing. He spent more than 4 decades inside the company. 40 years. Think about that for a moment. Entire industries appeared and disappeared while he was still learning how to improve yield rates by fractions of a percentage point. At advanced nodes, a 1% improvement in yield can mean hundreds of millions of dollars annually. That's why semiconductor companies don't just hire engineers, they inherit them. The problem for the United States is demographic. America stopped building large numbers of new fabrication plants for almost 2 decades. Between the early 2000s and the passage of the CHIPS and Science Act in 2022, manufacturing drifted toward Asia. Taiwan expanded. South Korea expanded. China expanded aggressively despite technical constraints. Meanwhile, many experienced American engineers reached retirement age with fewer young workers entering production-focused careers. Software looked more attractive. Finance paid better. Building chips meant spending years inside highly controlled facilities where even a speck of dust could destroy weeks of work. Writing code for a startup in Austin seemed considerably more appealing. China moved into that gap. The strategy wasn't particularly mysterious. It was patient. Companies linked to China's semiconductor ecosystem started targeting specialists in etching, deposition, process integration, yield optimization, and packaging. Not celebrities, practitioners. A former manager from a supplier company once described these people as living process manuals. That phrase stayed with me. Because manuals can be copied, experience cannot. Consider the case of memory chips. China's largest memory producer, YMTC, surprised many analysts by advancing faster than expected during the late 2000s. Several investigations later suggested that experienced personnel recruited from abroad had played roles in accelerating development, not because they carried secret blueprints inside their briefcases, but because they understood what problems were likely to appear 6 months before younger teams recognized them. Knowledge compounds, and timing matters. Remember the number 55 from earlier? Industry workforce studies show that a substantial portion of American semiconductor engineers are approaching retirement within the next decade. Some estimates suggest nearly 1/3 of the skilled manufacturing workforce could leave during that period. That creates a race. Not simply a race between Washington and Beijing, a race against time. The CHIPS Act allocated roughly $52 billion to rebuild domestic manufacturing capacity, and companies such as Intel, TSMC, Samsung, and Micron announced major investments in Arizona, Ohio, Texas, and New York. The facilities are coming. The question is whether enough experienced people are available to run them. An engineer cannot train a replacement overnight. Sometimes it takes years before someone learns why a process drift occurred, how contamination spreads between tools, or why a factory suddenly loses efficiency after changing suppliers. And there is another complication. Many veteran engineers genuinely enjoy teaching. After retirement, consulting offers can feel less like betrayal and more like continuing a profession they spent decades mastering. A person who dedicated 40 years to solving technical puzzles may not automatically view geopolitics as his responsibility. Honestly, I understand that perspective. If someone spent half a lifetime becoming exceptionally good at something, can government suddenly expect them to treat their knowledge as a national asset? I'm not entirely sure. But I do know this. Countries that lose manufacturing knowledge rarely notice it immediately. The decline feels harmless at first. Then, 10 years later, they're spending billions trying to rediscover lessons that once existed inside the heads of people they allowed to walk away. And the strange thing is that China may not need thousands of these engineers. It might only need enough to teach the next generation what America forgot was valuable. What makes this story uncomfortable is that the United States is not actually short of money. It is short of continuity. Washington can approve another subsidy package. Congress can announce another manufacturing initiative. Universities can expand engineering programs. All of that helps. But none of it creates a person who remembers what happened inside an Intel fabrication plant in 1998 when a process unexpectedly collapsed, or why a seemingly insignificant adjustment made in 2007 improved yields for years afterward. Experience has a nasty habit of refusing to accelerate. And this is where I think many discussions about China's semiconductor ambitions become too simplistic. The common narrative says Beijing wants to catch up technologically. That is certainly true. The Ministry of Industry and Information Technology wants domestic champions capable of competing with global leaders. SMIC continues refining its N+2 process technology despite restrictions. Huawei surprised observers by shipping smartphones containing domestically produced 7-nanometer chips in 2023, demonstrating that sanctions can slow progress without necessarily stopping it. But perhaps China is pursuing something broader: industrial memory. Imagine rebuilding an orchestra after firing everyone who knew how to play. You can buy the instruments, you can hire talented young musicians, you can even find the sheet music. Yet there will still be moments when someone asks, "Why do we perform this section that way?" And nobody in the room knows. Semiconductors work much the same way. People often compare fabs to factories making cars or appliances. I think that analogy understates the challenge. A modern semiconductor facility contains thousands of interconnected variables. Temperature fluctuations measured in fractions of a degree. Chemical concentrations adjusted by tiny percentages. Defect densities counted in particles almost impossible to see. Even experienced teams get things wrong. Taiwan learned through decades of painful iteration. South Korea learned through relentless investment. Japan once dominated memory chips and then watched its position erode over many years. Not because Japanese engineers suddenly became less intelligent, but because ecosystems weaken when enough expertise disperses and enough production migrates elsewhere. That history should make Americans pause. At this point, someone could reasonably object and say that China's strategy still faces hard limits. Advanced lithography remains unavailable. Restrictions imposed by the United States in October 2022 and expanded in later years complicated access to high-end equipment, design software, and certain categories of foreign expertise. I agree, China is unlikely to leapfrog the leading edge tomorrow. But that may not be the objective. Suppose Beijing shortens its journey by 5 years. Suppose companies like SMIC, YMTC, and emerging packaging firms avoid mistakes that previously consumed billions of dollars and a decade of experimentation. Suppose younger Chinese engineers spend the next 10 years learning directly from people who once helped establish America's manufacturing dominance. That changes the equation, quite a lot. And here comes the reversal. The engineers being recruited are not necessarily the architects of America's future advantage. They may be the custodians of its past advantage. The United States increasingly excels at designing chips. NVIDIA, AMD, Qualcomm, Broadcom, and dozens of AI-focused startups continue pushing computational boundaries. Yet manufacturing excellence depends on maintaining a culture where experienced practitioners constantly transfer knowledge downward. That transmission chain appears weaker than many policymakers assumed. My opinion is that Washington underestimated how strategic veteran engineers could become. Governments usually protect patents, software, and machines. They rarely think about protecting retirement-age specialists who simply know how things work. The doubt I keep returning to is straightforward. If the people who built America's semiconductor lead spend the next decade teaching someone else, who exactly is preparing the generation after them at home? Because one day those engineers will stop taking phone calls, and whichever country learned the most before that happens may inherit more than technical knowledge. It may inherit momentum. The interesting thing about inheritance is that nobody notices it while it is happening. You only notice it after it has already changed hands. Remember William Holt and the generation he represents? Their careers coincided with a period when the United States controlled nearly every layer of the semiconductor supply chain. American firms designed the chips, supplied the manufacturing tools, developed the software, produced critical materials, and still retained substantial domestic fabrication capacity. That ecosystem no longer exists in the same form. Pieces of it remain extraordinarily strong. Others were outsourced because it made financial sense at the time. Globalization rewarded efficiency. Shareholders liked lower costs. Consumers enjoyed cheaper electronics. There was nothing irrational about those decisions. The problem is that efficiency and resilience are rarely the same thing. A supply chain optimized for quarterly earnings doesn't automatically preserve national capabilities 30 years later. That realization explains why the United States suddenly appears willing to spend tens of billions of dollars rebuilding industries it once allowed to shrink. The CHIPS Act was not simply an economic package. It was an admission that some capabilities become difficult to recover once enough people stop practicing them. I suspect policymakers expected machinery to be the limiting factor. Instead, they may discover that people are. Intel's planned facilities in Ohio need technicians, process engineers, equipment specialists, and managers who have already solved problems younger employees have never encountered. TSMC's Arizona operations reportedly experienced delays, partly because experienced personnel were harder to find than construction funding. Money can speed up construction. It cannot compress 30 years of accumulated judgment into a 6-month training course. There is also something slightly tragic about the timing. Many of these veteran engineers grew up believing globalization would make technological competition less important. They entered a profession focused on improving transistors, not navigating strategic rivalries between superpowers. Then history changed direction. A retired engineer accepting a consulting contract in Shanghai may simply see himself as an engineer sharing expertise. Officials in Washington might interpret the same decision as a transfer of national capability. Neither perspective is entirely unreasonable, and that's probably why this issue remains difficult to discuss without turning every participant into either a hero or a villain. Most people are neither. They're professionals making personal decisions inside systems much larger than themselves. My prediction is fairly simple. Over the next decade, semiconductor competition will become less about who invents the next breakthrough and more about who successfully preserves and transfers practical knowledge from one generation to another. China seems determined to absorb as much experience as possible before that window closes. The United States appears to be racing to rebuild an industrial culture that once existed almost automatically. Maybe both countries succeed, maybe neither does. But I don't think 5 nanometers, 2 nanometers, or even angstrom-scale manufacturing will define the winner by themselves. The deciding factor may be whether younger engineers inherit decades of hard-earned lessons, while the people carrying those lessons are still willing and able to teach. That's my view, at least. And if I'm wrong, the evidence should become visible soon enough. New fabs will open, production numbers will rise, and America's manufacturing revival will look stronger than I expect. If I'm right, however, we may eventually look back and realize that the most contested assets in the semiconductor industry were never machines worth hundreds of millions of dollars. They were people approaching retirement age who still remembered why a process adjustment made 20 years ago prevented a factory from failing. Strange, isn't it? For decades, everyone talked about Moore's Law. We may end up discovering that experience has its own law as well. It takes decades to create, minutes to give away, and an entire generation to rebuild. If you enjoyed spending these few minutes thinking through the quieter side of technological competition, consider sticking around for the next discussion. The semiconductor race is often described as a battle over chips. I'm starting to think it's really a battle over memory. And memory, unlike lithography machines, cannot be sanctioned.